everybody, I'm going to go over pKa in this video. So pKa is really just a quantitative measure of acidity. It comes from the Ka, so it's just the negative log of the Ka, which you might have used in Gen Chem some. So the important things to know about pKa is really that if you've got a small pKa, that's going to equal a strong acid. Okay, so it's just the same as the pH scale, where as you go to those smaller, lower numbers, you're going to get the stronger acids. When you go to the higher numbers, you're going to have the weaker acids. Okay, so if we've got a large pKa, that's going to be a weak acid. Okay, and also as we've been talking about in terms of, acids and their conjugate bases and how stable they are and everything, that strong acid is going to give a weak conjugate base. So it's generally going to be a bad base, right? It's not going to be able to get reprotonated very easily. And that weak acid resulting in something from a large pKa is going to have a very strong conjugate base. So those are going to be the strong base type things, okay? So that's kind of important in terms of when we're talking about pKa, we're specifically talking about acidity, but it does tell us a lot about the potential of these molecules as bases in their conjugate base form. So you know that if you're looking at something that's a large pKa, then if you deprotonate it, right, which is going to be a little bit harder to do because it's a weaker acid, but if you get to that conjugate base, then you are holding a really strong base. So that's helpful to know when you're trying to figure out acidity or a basicity, right? So we can use the pKa scale for both of those factors. So one of the main reasons that we're going to use pKa is really to find equilibrium in a reaction. So we can kind of do this by comparing conjugate bases and the bases and kind of seeing, which one of these is the more stable side. But the pKa is nice in that it gives us a pretty quantitative measure of it. And you can, if things are closer, you can more easily say like this side is going to be favored. Reactants are going to be the main portion of this molecule at equilibrium. So we're going to use it a lot in that respect because it's a pretty handy way of using it. And pKa is just a very helpful measure that is going to help us in terms of adding on to what we've already been talking about in terms of looking at conjugate bases and kind of determining stability, looking at conjugate acids, determining stability. It's going to help give us a little bit of a double check here to make sure that we're on the right track. So for finding equilibrium in a reaction, we're going to look at a couple of options here. Okay, so the first option, we're just going to look at sulfuric acid Okay, so I've got sulfuric acid here, and we're just going to look at it in a reaction with water. And we're going to pull out our equilibrium numbers. So if I'm looking at this, hopefully we can kind of recognize a little bit. Sulfuric acid is a very strong acid. Water in this case is going to be more of a base than an acid in this regard. So we can have our water come and grab that proton. The electrons from that OH bond move onto the oxygen, and then we can draw our conjugate base and our conjugate acid. Okay, like that. So if we wanted to find where the equilibrium lies, and in that regard, we're really talking about, are the reactants of this reaction favored or are the products of this reaction favored? That's going to be where our equilibrium is going to lie. So the pKa can help us with that because we always want to be looking for the weaker acid, okay? So equilibrium is always going to favor the weaker acid. Okay, so that's what we are looking for here. So if we want to find that using pKa values, what we can do is we can go look at a pKa table, which I have one right here. So this is the pK table in Klein. It's in this chapter 3 of your book. And this is going to be one of the best resources that you have in terms of acidity and pKa. So the things that I really like about it is that it has the acid and the conjugate base. So it's basically telling you this is the most acidic proton in this environment, and it's drawing those all out for you, okay? Apart from that, it also labels strongest acids are up here, weakest base is up there, right? Because if we have the strongest acid, that means that our conjugate base is going to be a very, very weak base. And we can kind of see that just, you know, qualitatively in terms of the conjugate base for sulfuric acid. We have a very highly resonance stabilized anion here. I can delocalize that charge over 3 oxygen atoms. It's really, really, really stable. So that's not going to want to get reprotonated. You'd have to have a very, very strong base in order to reprotonate that sulfuric acid. Sorry, a really strong acid to get it reprotonated, to use that as a base. Got my words mixed up. So in the pKa table, we want to keep in mind that the pKa's are attached to the acid, okay? The conjugate base is here just to tell you, like, that is what you get if you deprotonate these protons that are in pink here. But you're really looking out for these numbers are connected to the acids, okay? So it's really important to keep in mind that the acids are going with the pKa's. The conjugate base is just a part of the reaction, but it's not actually, you know, in line with the pKa, right? It's related, but the number is not focused on the base. Okay, so what we want to do is using this pKa table, you can see it's fairly limited, right? We don't have everything on here, but one of the things that's important to note is that we have a lot of functional groups on here, right? So if we look through this, we've got a couple of the strong acids like sulfuric acid, HCl, we've got those types of things. We've got protonated water, so we have those options. But we also have, you know, a ketone when it's protonated on that oxygen. We've got carboxylic acids next to ketones or next to 2 ketones. We've got next to 1 ketone. We've got various types of alcohols. We've got alkynes, we've got amines, we've got alkenes. So we have a fairly big variety of options here that we can kind of see what the differences are like with those pKa's. So even if you don't have your exact specific compound on this list, then you can still kind of make an estimate and say, well, I have an alcohol, so it's going to be, you know, around 16-ish, and maybe if I have a little bit of resonance, maybe that number goes a little bit lower and makes it a stronger acid, you know. So you can still use it as pretty good guesstimate of the pKa's. And then in class, we'll also talk about the Evans pKa table, which is a much more complete collection of pKa values, but it's a little bit more advanced, but I want to make sure that, that we have a chance to look at it and play around with it too. So let's stay focused. So the pKa of sulfuric acid is -9, okay? So I'm going to just transfer that number up here. So I'm only putting it below my sulfuric acid because that is the acid that I'm using, okay? Then I need to look at the acid that is on this side, okay? So we're going to keep in mind here, we've got acid, base, conjugate base, and conjugate acid, okay? So pKa's are only with acids. So what I need to do next is I need to find the pKa for this hydronium, which is my protonated water. And if I go down to my chart, I can see that that is -1.74. Okay, and if you just go to 2, I don't care, we can round it. And so then what we want to be looking for is the equilibrium is always going to favor the weaker acid. So we ought to make sure we remember our negative number line. and we're thinking about bigger numbers, are going to be the weaker acid, right? So in this case, this is our bigger pKa, right? This is our most acidic. The water protonated is our least acidic. So we're going to favor the products here. Okay, so we can also go ahead and change that equilibrium arrow and make it a little more unbalanced and say, I'm more favoring that product side because that's where my weaker acid is lying. Okay, so that just tells you that in a beaker of this stuff, you're really looking at, okay, if I've got these two things together, I've got sulfuric acid and water, what you're mostly going to have floating around in that flask are these structures. So you've got the conjugate base of sulfuric acid and you've got the protonated form of water. Okay. So let's look at another example. So if I have this deprotonated ketone, this is called an enolate, but we will talk about the enolates more next semester. Okay, so if I'm looking at this, I have a negative charge on my ketone, and then I've got a neutrally charged amine. Okay, so in this case, I'm actually going to be using this as, oops, not that, as my base, and my amine as my acid. Okay, just because I'm going to use the most basic atom, which in this case, we're going to consider to be the carbon. So I'm going to go grab the H on this other compound. This is diisopropyl amine. So now I've got 2 protons on that ketone, and I have deprotonated my amine. Okay, so if we go ahead and look at this, I did that really. So if we're looking at this, we need to again label out our conjugate base and conjugate acid. So this is our conjugate acid. This is our conjugate base. And then I need to find the pKa values for both acids. So the acid and the conjugate acid. So down here I have basically an amine type of structure. So let's go down to our pKa table and find an amine. So I've got one way down here. And you want to make sure that you're looking at something that looks like this, not something that looks like that. Okay. So that's the one on the left is what we want to be matching the structure to. So it's about 38. And again, mine is different, right? So this acid that I have here has some alkyl groups on it. I'm not terribly worried about that. It's still going to be pretty close to 38. Okay, so then I need to look for my conjugate acid, which is going to be protons next to a ketone, something like that. So if we go look down, I've got a ketone right here. That's a pKa of 19-ish. And again, this ketone is different from what I have, but they're going to be very similar in their conjugate base structures and how they stabilize charges. So my acid over here is a pKa of about 19. Okay, so if I'm looking at these and I'm looking for the weaker acid, that is certainly over here, right? So as I have drawn this reaction, what's actually going to be favored are the reactants. Okay, so if I change this arrow up, I'm really more favoring the reactant, the starting material side, rather than the product side. So here the reactants are favored. And if I just switched the way I wrote this reaction and I had it this on that side, then it would be products favored. Okay, so it really just depends on how you write the acidity, the acid-base reaction in a whole. So products or reactants can be favored depending on how you set up your reaction between base acid and conjugate base conjugate acid. So just a couple of wrap-up points here. So again, I've kind of said it a few times already, but pKa is only belonging to acids. Okay, so in any acid-base reaction, you're going to have two of them. So one is going to be for the acid and one for the conjugate acid. Okay, we're actually not considering the bases at all here. And then the last point is that using this can really help you to answer the question of, is this base going to be good enough to deprotonate this acid? Okay, so it can help answer the question of picking a suitable base for a given acid. Okay, because if you go and pick something and you set up your reaction like this, and you're trying to say you're trying to deprotonate that amine, but you're trying to use that deprotonated ketone as a base, that's not going to get you very far, right? They're just going to mostly stay in that starting material phase and not ever do the acid-base reaction that you're wanting to do. So you can make sure that you're stacking the deck in your favor by making sure that you've got a strong enough base, you've got an acid that's going to be compatible with that, and then you're going to be able to get to, you know, the deprotonated or the protonated product that you actually want. So with that, let me know if you have any questions, and we will obviously keep practicing this in class, and I will see you all later.